Hello everyone, welcome to this webinar. In this webinar, we're going to learn a little bit more about Apache Dremio and Dremio products and other Apache products. This webinar is called Data Reflections, Accelerate Your Queries Without Copies. Now we're going to introduce the people that are going to be talking in the next slide. So my name is Jesse Anderson. I'm the Managing Director at Big Data Institute. I'm also a committer on Apache Beam, and I've contributed to other various open source projects, especially Apache projects. You might have read some of the writing I've done on my personal site or on O'Reilly. With me is Stephen Phillips. He's a principal software engineer at Dremio. He's also a very technical person. He's a PMC and committer on the Apache Drill and Apache Arrow projects. We're in good luck because we're able to, as technologists, ask some very technical questions to Stephen. So be ready, let's try and stump him with some really technical things. So now, speaking of questions, here's how to do your questions. I'll be monitoring this as kind of the moderator for this, and then as I see questions pop up, or as I see something that we want to cover, we can do that. So if you want to, in the Q&A, if you see the Q&A at the bottom, it'll look a little bit different on yours, but please do avail yourself of the ability to ask questions. With that, I'm going to turn it over to Stephen. Stephen, thank you.
Thank you, Jesse. To get started, I want to give a little background for why are reflections important. So it all starts with the raw data. Organizations now have lots of data in lots of different formats all over the place. And it could be databases such as Hadoop or Microsoft Azure, Amazon S3, and a bunch of spreadsheets in various places, and it can be very disorganized and hard to manage. And especially if we want to be able to get insights from this data, for use by data scientists or BI users, there's often a very long and expensive process to make this data accessible. On this chart here, we kind of have a couple of different layers of data transformations. And so sort of the lowest level will be the data lake. This is a very raw, unstructured data, often very messy. And some of the aspects that are of this data in the data lake is that it often involves custom ETL. And these transforms can be very fragile, they break easily, and it's also very slow moving. So, and then typically the way organizations will then, try to wrangle and manage this data is by, moving some of this data into data warehouse or data marts, such as Teradata or Vertica. Some of the disadvantages of this, though, are that first off, they're very expensive. And there's a lot of overhead, and obviously these are proprietary. There's lock-in. This can create some problems for the organization. And even then, the data still isn't maybe doesn't quite satisfy the needs of the BI users and data scientists, and that these queries may take too long to run or use too much resources. We can't have BI users hitting the Vertica instance over and over again, and it might just cause too many problems. So the next step that organizations typically have is some sort of copies of the data into different formats that the BI users can use, and this includes things like cubes or Tableau or other BI tool that may have extracts and so on. Now the problem here is that now we've got the data sprawling. It's copied in many different locations. Governance becomes a problem. Trying to manage and keep track of where all these copies are located and stored is a real headache. And then it's slow to update. And if you need to modify, if you need a new dimension in your query or whatever, it can be a very long and drawn out process to have the data engineer modify the cube appropriately for the BI users or data scientists' needs. So this is kind of the current normal, I guess, for how large organizations manage their data and make it accessible to the end users. So And BI users are getting left behind here because it creates many headaches for them. First off, they're dependent on IT to manage this for them. They need IT. They have to ask and have IT find, access, and prepare the data sets. This slows down their access. And some of the data in its raw format is really not very accessible to the BI users. For things like Hadoop and JSON, Parquet are some examples. And this leads to long lead times. It can take even months to onboard new data sets and change, or even just modify or change the level of detail for some of the cubes that or extracts that exist. So there is a better way. That's why we built this company and product Dremio. It's designed to work with any data lake, any BI or data science tool, and it can provide 10x to 1000x data acceleration. Dremio is considered a self-service semantic layer, and this is based on zero-copy data curation, and it's a very expandable. It's a scale-out architecture. You can run it on just a handful of nodes, and you can scale it out to over 1,000 nodes. And it's built on open source software, and it is itself open source. So Dremio represents a new tier in data analytics, and we like to call this self-service data, or also known as data as a service. So as you can see in this diagram, at the bottom we have our various data sources. Things like Hadoop, MongoDB, or various relational databases. At the top, we have the data science and BI analytics users. So they're going to use things like Python, maybe with Pandas, or R for the data scientists, and the BI users typically use something like Tableau or Looker. And Dremio sits in between these two, and it provides various things. And the one I'm going to focus on mostly today is the data acceleration component of what Dremio provides. So the one way to think of data reflections is as a relational cache. So I'm going to kind of go into a little bit of depth about what relational caching means. So first off, we have there's a little refresher on what are some of the key aspects of relational algebra. So first off, you have relations, which are basically tables, or in other words, a set of tuples is a relation. And then we have various operators, and these define some set of transformation. Some examples of an operator might be a join, project, scan, filter, aggregate, window function, etc. And then we also have rules, which are used by the optimizer. A rule defines a logically equivalent transformation of a plan. So for example, you may have a project followed by a filter operator, and then the rule can determine if it's logically equivalent to perform the filter before the project, or vice versa. And there are a lot of different potential rules that can be used to optimize a query. And one other term to understand is a graph or a tree. So in relational algebra, this sort of pipeline of operators can be represented or thought of as a graph. And specifically in Dremio, it was known as a DAG, or a directed acyclic graph. So on the right here, we actually kind of have a couple of very simple graphs. In this case, it's a scan, project, and filter. Or logically equivalent tree is a scan, filter, project. So those are examples of query plans or DAGs. So what is a relational cache? So a relational cache is a little more sophisticated than just a basic cache. A basic cache might be just store the result of a query, and then if you run that same query, return the results that you cached. We want to go beyond that and store the data in some sort of an intermediate state. The advantage here is that the cache can then be used to satisfy more queries beyond just one simple query that we that we cache the results for. So there's a concept that we like to use, which is distance to data, DTD. So originally, if without a reflection, without the relational cache, then the original distance to data is much larger. We can go from the original data at the bottom of this graph, and then up to something what you want. The idea is then we can persist some intermediate state that maybe isn't quite exactly what you want in any case, but is much closer. And then the queries that then when a user actually runs the query, the new distance to data is much shorter than it was with that originally. And so by doing this, we can now satisfy a wide variety of queries with this cache. They will all be accelerated, and it will reduce resource requirements and latency. So to some extent, you probably are already doing this manually. This is typically done with things like sessionization or cleansed data, or maybe you in your data warehouse or data mart, you've partitioned by some time or region, or maybe you have some summary tables that are summarized for a particular purpose. And now currently what this means is the user will have to choose what to query depending on what they need. The analysts have to be trained on using different tables depending on the use case. And often there are going to be custom data sets built just for reports. And this might include things like summarization or extracts built for things like Tableau dashboards. Okay, so let's compare the two models. Like we might call the current model that is often used as copy and pick, whereas what Dremio provides through data reflections is the relational caching model. So on the left, you can see the copy and pick, where on the bottom we have our original raw data. And then we sort of have the physical layer, which is represented by the various cubes or view or extracts or whatever that the admin has created. And then there's the logical model, which in the copy and pick world is the same as the physical model. There is no difference. The end user will then go and pick which physical optimization to use to satisfy their logical use case. In the relational caching model, there is a separation between the logical model and the physical optimizations. So we do have various physical optimizations in our relational cache, but the end user doesn't need to know about them or care about them. They're simply going to look at the original data set as a logical in the logical model, and then the relational cache itself will figure out how to leverage the physical optimizations to satisfy the end user's needs. So let me describe a few of the key components of relational caching, and specifically what we use in Dremio reflections. So first off, in order to express the transformations and states, it's just a part of Dremio SQL language. In order to match the relational algebra to determine if a reflection can be used, we use a library called Apache Calcite. The reflections themselves, the materializations, are persisted in Parquet. Parquet is this is also another Apache project, which provides on-disk columnar storage. And how we process the data is through a combination of Apache Arrow, which is the in-memory columnar format, and Sabot, which is Dremio's query execution engine. And of course, we have a lot of code putting it all together, as you can see from this diagram. I won't go into a lot of detail on this, but this is kind of the high-level architecture of how the relational cache works. So let's talk a little about reflection definition and matching. So first off, coming back to Calcite, like I said before, Calcite is an Apache project. it is a planner and an optimizer, and also a SQL parser. And it comes pre-built with many of the things that are needed for optimization, such as operators, the various rules that we described earlier, and things like properties, which includes things like distribution or sortedness, collations, and so on. And it has the ability to handle materialized views, which basically, if you're familiar with the concept of materialized views, the relational cache is a very similar concept. So this provides a perfect foundation for relational caching. So here's how we built the cache. And we call them reflections. And essentially a reflection is a persisted alternative view of data stored in a Parquet format. And we have two types of reflections. One is a raw reflection, which persists all the records of the underlying data set, but allows you to control how you partition and sort the data. And the other type of reflection is the aggregate reflection, which persists a partially aggregated data set based on a selection of dimensions and measures, which also allows partitioning and sortedness. And these reflections can be built on top of either the raw source tables or some what we call a virtual data set, which is somewhat analogous to a database view. So I'll give some examples of how this works. So here, let's say we have a query. On the left, we have our user query, which involves a scan of some table called T1. We then project the columns A and C. From there, we perform an aggregation where we group by A and compute the sum of C, rename it as C prime, and then filter, keeping only the records where C prime is less than 10. This is a very simple example. Okay, now inside the reflection definition, we have a similar query where this time we simply did a scan of T1, and then an aggregation where we grouped by A and B and computed the sum of C. So you'll notice that the query is not exactly the same as the user query, but it's very similar. Okay, so now this reflection definition, what it means is that that target query can be replaced with a simple scan of the materialization R1. All right, so then using our Calcite-based reflection matching algorithm, Dremio is able to figure out that we can rewrite the original user query using the reflection R1, and the plan is now scan R1, aggregate on A, compute the sum of C, and then perform the filter where C prime is less than 10. So this new query looks very similar to the original, but one thing to note is that instead of scanning T1, we are scanning R1. And depending on the data, R1 could be 100,000, even 1,000,000 times smaller than the original T1. And so because of this, our optimizer will look at the various plan, at this alternative plan, and say, oh, this is much cheaper, much better plan. Let's use this. And then this query could then be correspondingly 100,000 or even 1,000,000 times faster. It depends on how much reduction we get when we created this reflection, based on the cardinality of the dimensions that were specified. Here's another slightly more complicated example. In this case, the user query involves a join of two tables with an aggregation after the join. Now, but our reflection does not have the join. It's only an aggregation of T1, which is one side of the join. Well, our algorithm is smart enough to leverage this one as well. And it turns out then we can replace the left side of the join with the aggregated version with this reflection, which contains the aggregation of T1. And most likely in this scenario, T1 is a very large table, and T2 might be a dimension table. So we didn't see a need. We didn't have any need to create a reflection for T2 because it was small enough. But T1 might be very large, and so once again, this could be a very big improvement over the original query, because R1 could be 1,000 times smaller than T1, depending on the data. So in both of those previous examples, we used aggregate reflections. In this example, I'm showing the benefit of how you might use a raw reflection. So this is a very simple query. Just a scan of T1 and then filter some filter condition on column A. And sometimes this might be referred to as a needle in the haystack query, where maybe we're trying to find just a few records out of billions that match some filter criteria. So now in this example, we actually have two reflections that are being considered. The one on top, we do a scan of T1, and we created a raw reflection. So in this case, the raw reflection is equivalent to the original table, but we also keep track of the fact that for R1 it is partitioned by A, and we have another definition which is also a raw reflection, but in this case is partitioned by B. And so both of these reflections will be considered, and then our optimizer will notice that, well, if we use the first reflection, and since our filter depends on column A, we should be able to prune. We will be able to prune out much of the data if we use the first reflection, and therefore it'll be much cheaper to use that one. And our optimizer will choose the R1 instead of. I think there's a mistake there. There should be R2. Anyway, it'll choose the top one where it's pruned on A. And then the final example I want to show here is a relatively new technology that we developed. And this is called we call it the Starflake feature. So in this case, imagine we have a user query. Well, actually, let's start with the materialization definition. So imagine you have a sort of a star or a snowflake schema that defines the various tables in your raw tables. So in this case, we have a F1 as a fact table, and then we might have D1 and D2 as dimension tables, which are then joined together. So now let's say you create a reflection on top of the join of those three tables and call it R1. Now, if some user comes in and they run a similar query, but they don't include D2, they're just joining one of the dimension tables with the fact table. Well, our Starflake will be able to determine that based on the fact that these are dimension tables, this join is a cardinality preserving join, and therefore we can still use this materialization even though the user query is not using all of the data from the reflection. All right. Another thing I'd like to go into now is how do we keep these reflections up to date as data is modified or added to the underlying data sources. So first off, we have the refresh management. Okay, so the underlying data may change, and the user or the admin will need to define a refresh frequency for the underlying data. So for a highly changing data source, they would probably want to have a more frequent refresh frequency. And they also need to define sort of a TTL, which defines, at what point, if the reflection is beyond some age, then we should not use the reflection because it should be considered stale. Another thing that is important about how we do the refresh, we manage these refreshes, is that it's possible that one reflection could actually use some other reflection as part of its refresh. So we make sure, using what we call a dependency graph, to order the refreshes appropriately. And the simple example would be, as you see in this diagram here, if we have a physical data set and we created both a raw and an aggregate reflection, most likely the aggregate reflection can actually use the raw reflection for its refresh. So we will make sure to first refresh the raw reflection, and then once that is done, refresh the aggregate reflection. And then we have multiple update modes, which this is something the admin would have to figure out based on the underlying data. The simplest one is what we call a full refresh. And this would be appropriate when the data, underlying data is highly mutating. So if it includes updates or deletions in the underlying data, then the update mode would be full update, which basically means every time we refresh the reflection, we will rebuild the entire thing from scratch. However, in many cases, we can be better than that because if it's known that the underlying data is append-only, as in we're only adding new rows to the data, we're not doing updates or deletions, then it makes sense to not recreate the entire reflection every time we refresh, but only add the newly added data. And the two ways this is handled depends on what type of data source we have. If it's a file system based, then we can simply look at the timestamp or the create time for the files and only add the data from the newly added files. If the underlying source is something like an RDBMS source, the way we handle this now is the user can define some column or key that is monotonically increasing. This could be like a timestamp is a common one. As new data is added, there's always the timestamp field is always increasing, and we use this field to only add the new data every time we do a refresh. Okay, so I want to go into a demonstration now of how these reflections can be used to accelerate your queries. And so the data set I'm using is it's from New York City Taxi, and it's the data collected for all the taxi visits or taxi trips from 2009 through 2014. This data set contains about 1 billion rows, which corresponds to about 180 gigabytes of data, and it's in the CSV format. And a CSV format is not a very efficient or performant way to store the data. The Dremio cluster is running in the Google Cloud. It's a pretty small cluster. Just has one single coordinator node and 2 executor nodes, each with I think 4 cores. So a pretty small system. And so 180 gigabytes for this type of for this small of a cluster is a pretty sizable data set. So let me go ahead and switch to my Dremio UI. Okay, so here I've opened up the UI to the page where I'm viewing this table called trips, which is a slightly cleansed version of the raw CSV data. Real quickly, I can show you what the actual underlying SQL for this data set is, and you can see that we are doing some various conversions and a few cleansing queries. Okay. Okay. So, but I'll go ahead and hide that for now. The nice thing about virtual data sets is that you can then, once you've done your cleansing query, you can ignore it. So this is what the data set looks like after having cleansed it. So you can see here we have a few columns of interest, a vendor ID. More interesting, we have the pickup date time and drop off date time, and then a bunch of other stuff like passenger count, trip distance, a few more columns. Also of interest is the fare amount. how much was actually paid for this for each trip, and then also a breakdown of things like surcharge and tip. Okay, so this was done in advance to make it this demo go more smoothly. But if you want to create a reflection for this data set, you can click on the gear up here at the top and come down to the reflections tab. And you can see here, there's a button here for raw reflection and also for aggregation reflections. Now, these columns were actually suggested by Dremio as an appropriate or possibly good choice for what to use as dimensions and what to use as measures. And in this case, I just went with the recommendation because I think they look pretty good. Looking at what we have for dimensions. Now, keep in mind, when we say dimension, a dimension is what column do we expect to typically group by when analyzing this data. And measures it means what are the columns that we typically expect to compute values for. And what we're typically computing is going to be things like sum, count, and average are the more common ones. Okay, so I previously already created these reflections, but I just wanted to demonstrate how one would do this. And if you wanted to modify this, it's very easy. You can move these around, create different dimensions or different measures. I'm going to go ahead and cancel. Now, like I said, the original data set was a 1 billion row, 180 gigabyte data set. So running some simple queries would actually take quite a while. For example, what if I just wanted to get a list of the distinct vendor ID? Well, I'm going to run this right now, and it should be very, very fast. See, it came back in less than a second. Without a reflection, this would take much, much longer. Because first off, because the underlying data is CSV, it would have to read all the data. Even though I only care about vendor ID, the CSV format basically requires us to read 100% of the data. And then it has to parse it and then aggregate it over 1 billion records. And this would take, I'm not sure how long it would take actually, but it would take quite a while. But you can see here with the reflection, it's much, much faster. Okay. I'm going to show you the jobs page. So Dremio lets you look at all the jobs that have been running. And if we click on here, we can actually look at a profile for the job. And I just want to demonstrate here that we can see first off, we can see from the plan that the original plan is much more complicated, aggregate on top of project, and then going all the way down to having a filter and then the underlying data source, which is the CSV with 1,404 files, or splits, actually, sorry, those are HDFS splits. But with the reflection, the optimizer ended up choosing a plan that queries the reflection instead. And first off, it's a much simpler plan. And then we can also look and see, if we click on the stats, we only read a few 100,000 rows, whereas the original data set has over 1 billion rows. So we can see here that we probably had more than a 1000x speed up in this query. So I'm going to show now how this is useful and how we integrate with popular BI tools. So specifically, I'm going to look at Tableau. So we actually have, for when viewing a data set in Dremio, you can then click on this Tableau button up here, which will download a TDS file, which you can just simply click on, and it will, assuming you have Tableau installed on your system, it will launch Tableau and prompt you for your credentials. These are your Dremio credentials. Oops, mistyped it. Okay, Tableau just crashed. Let me. Okay, yeah, it's working fine. I don't know why I got that error, but so now that I'm in Tableau, I can start doing the typical things you might do in Tableau. So let's start by, I don't know, let's drop a number of records here in columns, and notice how quickly this returned. Very snappy, and we can see the count is over 1 million. Okay, so now let's say, well, I don't want just the number of records. Let's look at the number of records grouped by year, for example. So let's grab the pickup date time, drag that over to rows. Let's change this to a bar graph. Okay, so now we can see that the number of pickups as a function of year seemed to have picked up a little bit in 2012, but then maybe it's dropping off in 2014. Kind of interesting. Maybe I want a different granularity. So let's come here and choose a different, maybe by month. Actually, no, let's do this one. So, but first off, I'd like you to notice how quickly these are returning. It's basically an interactive experience. That's kind of cool. Maybe we want to look at the average fair amount. There we go. So we can see that the average fair amount seems to be increasing. And in fact, there's a big jump around September 2012. Kind of interesting. I have no idea why, but this could be the beginning of some investigation into why that is happening. So that's, and then we can then go back to back into Dremio and look at the jobs page again. And we can actually see the queries that were generated by Tableau. And we can see that they are all able to use the reflection, and they're all completing in less than 1 second. And believe me, without the reflection, this particular Tableau use case would not be interactive at all. We're looking at probably minutes every time we drag something. So I hope this is a good demonstration to you of the power of Dremio reflections in making the BI user experience better. So that's the end of my demo. So let me go back to the PowerPoint. There we go. So now we have a time for Q&A and also some closing words. So please notice these links. I think you'll find them very interesting. First off, we have Dremio University, which contains lots of great content for how to use Dremio, and also just general big data analytics content. Also, definitely download Dremio. We have a free community edition. It's open source, so definitely download it and try it out. And the library, actually, I don't know the library. Yeah, check these links out. And so now I think we'll have a chance for take some questions.
Yes, a few questions that popped up. Are you able to show in that in the Dremio UI how long it took you to ingest that initial data? You were saying that you didn't want to show that because it took a bit. Exactly how long did it take?
Oh, so for this one, it took about an hour. But how long it takes, that is obviously highly dependent on the size of your cluster. So like I said, this is typically Dremio clusters will be more than 2 nodes. I think my cluster is the smallest size that GCE supports that Dremio allows. We have some minimum requirements, and I think something like 8 GB of RAM or something. I forget the actual number, but very small instance. It took about an hour for this particular query.
And for a production cluster on average, how long do you think that would actually take?
Well, it's very scalable. So if you had a 10 node cluster, it would take probably 5 times, 5 times as fast. So you go from an hour down to maybe 20 minutes. Now, typically, people or users will schedule their refreshes to happen during less loaded times, like maybe overnight or whatever. So it's expected that the reflection will take longer. The reflection refresh will take longer than the actual queries because we're doing more of the work up front.
Yeah. Okay, another question from the audience. Materialized views will initially take time to instantiate. How do you manage this in a production system? Do you need to warm the system with the expected user queries to allow materialized views to be initially created?
That's a very good question. So right now that's basically how it would work, and it's not even automatic. We do have some suggestions that we'll make for what for a given data set, what reflections to choose. But it's somewhat going to be a manual process of looking at what queries you've been running and trying to determine what the optimal reflection layout would be, what dimensions and reflections, or what dimensions and measures to choose. That being said, we're definitely working on more a better automation of this, so that Dremio will figure out, based on the workload, what are the optimal reflections to create.
Excellent. Another question: maintaining materialized views can consume considerable space. How are storage limits managed? Are unused materialized views ever GC'd or garbage collected?
So yeah, they can use space. So right now it's somewhat manual. We do have some pages in the UI which can tell you what the footprint for the various reflections are, and I think we have statistics that allow us to see what reflections are being used and what are not. But right now it's not automated. It's not automatically pruned by the system. It'll be manual. So yeah, that's right now. Yeah, it's not automatically to removing the unused reflections. But that would definitely be probably a useful feature for us to add.
Perhaps a follow-on question to that they didn't ask. Which parts of the data are stored in Arrow, so i.e. in memory, versus on disk?
So yeah, that's a good question. We actually store it all on disk. So Arrow is simply the format used in memory during the pipelining. We don't currently cache we don't currently store any of them on disk. We don't currently store any of them in Arrow in terms of where we store the data. So that's one thing to know, is it's not an in-memory cache. It's a on-disk cache. Straight on disk.
And then the actual storage, is that in HDFS or is that in a local file system?
So it's configurable. It's best if it's either an HDFS, or if you're running in a cloud environment, then it probably makes sense to store it in the cloud storage like S3 or Azure Data Lake. So yeah, we did that's generally the vast majority of customers will either do an HDFS or in the cloud storage. And there is an option for storing on local disk on the local nodes for all the Dremio executor nodes. The disadvantage there, though, is that you lose out on the replication persistence that you get with HDFS. So that's not our recommended configuration, but it is supported.
And you didn't talk about it specifically. Is there a specific flavor of HDFS you support, or is it all of the HDFS versions?
So I mean, all. Well, I don't want to say all, but most of the common ones. So we specifically have tested support for Cloudera, Hortonworks, and also MapR distributions of Hadoop. Those are all supported.
And EMR, I know you can spin up HDFS with EMR. Do you support that as well?
EMR is also supported, yeah.
Okay, great. Okay, and then another question asked is there downtime during updates to reflections? Say we want to refresh every 5 to 10 minutes.
It's not downtime. However, the refresh itself can consume resources, and so you might see some impact to other user queries that are running while the refresh is happening. Now, we do have workload management, which can help manage that. Generally speaking, we'll give current user queries higher priority to reduce the impact of the refresh. So generally, there shouldn't be downtime. That being said, though, often customers do decide that it makes sense to run their refreshes during non-peak hours. But it's not downtime. The cluster is still accessible and usable.
Another question that I think is related to that question is concurrency. You didn't really talk about how many concurrent users could you actually run at this?
There's no hard limit, but we've definitely been seeing our customers run with 100 concurrent queries,
Okay.
our end users. So.
Excellent. Yeah, that's been one of the kind of missing pieces out there in the ecosystem of how to do BI queries concurrently at large scale. So great. Okay, the next question is, what was the max memory allocated for Dremio?
So I'm guessing they're talking about just in this particular example. I think I said 8 gigabytes earlier, but I think it's actually 16 gigabytes is the memory on these GCE instances, and most of that is allocated for Dremio. However, these queries, I don't know that they were using anywhere close to that.
So to be clear, those Dremio processes are Java processes, correct?
Yes, they're Java.
And maybe asking about the JVM XMX.
So actually, one interesting thing about Dremio is that it's not just XMX, which limits the Java heap, but especially on the executor side, we actually do most of the memory we consume is not heap. It's direct memory.
It's off heap?
Off heap memory, yeah.
Okay.
So there's a separate setting for that, which to limit how much off heap memory we can use. But typically, an executor node will recommend, I think. Well, this is a pretty small node, so I believe we're doing basically 4 gigabytes for heap and 12 for off heap, because all the actual data buffers are off heap. The heap is only used for some of the control structures, but the actual data itself is in off heap buffers. So as you get more production, in a production environment, you're typically going to have quite a bit more memory, and the vast majority of that will go towards off heap, because that's what allows you to increase your capacity for running a lot of queries. Usually, the heap is not where most of our memory is used.
So to be clear, the executor's off heap usage is more for the aggregation. So it's, for example, if it's doing a distinct, it's storing those distincts, the actual distinct value as well as the count, for example, in that off heap.
Sorry. What I meant is all the arrow buffers, all the data so when we read from Parquet and we load the data into arrow buffers, all those the buffers themselves are off heap.
Okay.
And then as the data flows through the pipeline of operators, they'll be transformed and new data will be written into new buffers. Those are also off heap.
I see. Okay, and the next question is, the scheduler is by a number of hours instead of a specific time. Is scheduler going to be updated to allow specific time scheduling of reflections?
I believe that's been asked for, and I think we are working on that, but I can't give a specific timeline for that at the moment. But I'm pretty sure that is in the works, because I know customers have asked for that.
Okay. Answer that live. Okay. You talked a little bit initially about who the primary users of Dremio are. Oftentimes it's the data engineer, putting that data into Dremio, loading that into Dremio, and then from there, the business intelligence and data scientists are using it. Are you finding that data scientists are using Dremio for discovery?
That's a very good question. Unfortunately, I'm not the right person to answer that one. I'm on the development side. In terms of whether or not that's happening, I honestly don't know. That would be something I could look into and talk to someone who's more on the sales engineering side, or possibly our product side would know the answer to that. I would think probably some are doing that, but I can't say for sure.
Okay, and it sounds like, given your level of integration with Tableau, that it's very, very common for the BI folks to be querying against Dremio with their Tableau instance.
Yes, yeah, that is very. I have seen that for sure at a lot of our customers.
Okay.
Tableau does seem to be the most popular of the BI tools I've seen, but we also support. I mean, we support almost any of them, but our best integration would be things like Power BI is another good one. Looker, we have integration with that. I think MicroStrategy, but yeah.
Okay, and somebody asked about this being made available for offline viewing, and the answer is yes. The attendees of the webinar will get a copy of, or get a link so they can watch this again. Kind of speaking of that, let's say somebody has a question or wants to reach out to you. Is there an email address that they could reach out?
You know what, there is. My email address is Steven with a V at Dremio.com. I don't know if I can just add it to the slide or no. Okay, so
I will chat it out as well.
Yeah, chat it out. Like that would have been. I should have added it here. So.
Okay.
We also have a Dremio community forum. Also would have been good to add the link here. But I think if you just go to our Dremio.com, you should be able to find a link to the community forum, which can also be a great place for asking questions, because we, not just Dremio employees, but also other paying and non-paying customers contribute to the both asking and answering questions on the forum. So.
Okay, there were two other questions. I didn't see them because they were in the chat instead of the Q&A widget. So the one question is Dremio a replacement for the traditional data warehouse? Does we'll start with that one. That one's a good initial question.
I would say no, it's not a replacement for data warehouse. We envision it mainly as supplemental or possibly living side by side. Generally, I don't think we really would recommend that you would want to just replace your, generally speaking. For some specific use cases though, it might make sense to move that use case from your data warehouse into Dremio instead. And the reason for that is maybe like data warehouses like Vertica, Teradata, they do provide things that Dremio doesn't have, but they're also very expensive and cumbersome and difficult to work with. And if you don't need all that, if you don't need the data warehouse, then Dremio could definitely be a replacement for certain use cases. But generally speaking, no, it's not a replacement, it's a supplemental.
Yeah, I think that's one of the things I would recommend people take away from this is there's a desire from management and often from database people to have a single place for everything. That just isn't going to work in big data and at scale. There's just too many trade-offs, as you mentioned.
Yeah. One thing to note, we actually support Teradata, for example, as a input source to Dremio. So.
Okay, the other question is, does the relational cache essentially copy all of your source data into memory? I think you kind of answered that one already.
Also, two things I noticed is that it's not really a copy. And first off, it's not in memory, it's in the disk. But even so generally speaking, you're going to be doing aggregate reflections to get the biggest bang for your buck. And that's not a copy, it's a pre-computed, partially pre-computed aggregation. So generally it's much smaller, orders of magnitude smaller than the original data. And even in the case of a raw reflection, typically you're not including, like, from what we've seen at most of our customers, typically not every column in the raw data set is even necessary for analytics. So it's not going to be a naive copy of the entire data. It will only be the copying of the columns that are needed, which is then, you know, compressed using things like dictionary encoding and other types of compression. So typically, even in a raw reflection, the footprint of the reflection is, you know, many times smaller than the original data. So one way to think of it is that a reflection is more like building an index than it is simply copying a copy of the data.
Okay. And then they ask another question: what's the largest production Dremio implementation in terms of both source data and varied numbers of data sources?
Oh, that's a...
That one may not be one you know as well.
So if by implementation, if they mean like, we've definitely had, you know, I know of a customer who has a 600 node Dremio cluster with, I believe, multiple petabytes of data. That's the largest one I know of. In terms of number of data sources, yeah, most of our customers don't usually have a huge number of data sources. There's nothing stopping us from supporting, you know, 100 different data sources. I just haven't seen that being usually the case. Typically, it's a much smaller number, but there's no reason it couldn't be hundreds.
Is there an estimate on what that 600 node cluster is? That a petabyte? Is that 2 petabytes?
It's in the petabytes. I don't remember how many petabytes, but
okay, that's usually what
the petabytes is the data in the underlying HDFS that we're connecting to, or the Hive. Sorry, it's actually a Hive, kind of a Hive Apache Hive formatted data that we've used Dremio to run queries against.
Okay. Yeah, usually those sorts of questions are that they're just trying to get an idea of the high watermark to make sure that they're under that. There is one more question that we haven't talked about, and that was Spark integration. Oftentimes the data scientists and data engineers will want to query Dremio with Spark. Could you talk a little bit about that?
Yeah, that's a good question. As far as I know, it's not my area of expertise, but I know that we do have ways of connecting Dremio as a source inside of Spark. So you should, I forget which how that works though, but there's not. I guess I should be honest. I don't know that there's that much integration currently, other than being able to add Dremio as a source. I guess we kind of view Spark and Dremio as being like coexisting. We can use one or the other. Now, one interesting thing to note though. I didn't get into this in the slides, but we actually have another feature called external reflections, which allows a user to manage the creation of the reflections themselves using. So maybe they would use Spark or Hive to actually create the reflections, but then register them in Dremio as being equivalent to some other query, and so then it can be used for substitutions, but it's maybe you already have the data generated through some other Spark job or something. So that's one example of how Spark and Dremio can work together.
Well, excellent. Well, we are out of time. I'd like to thank you, Stephen, for taking the time to tell us a little bit more about Dremio and how we can start using that. And hey, there's some pretty cool things that we can do and how fast it can happen. So I think that was definitely what I took away of. I'd love to see my BI people spending a lot less time waiting for a query to come back. So with that, I'd like to thank you for Dremio, Stephen, and so on behalf of myself and Dremio, thank you again for attending, and we wish you the best of luck as you implement your Dremio solutions. Thank you.
Thank you. Thank you, Jesse.